electroscope quiz. Where would the electrons in this electroscope go if a positive rod came near? So what do you think? Let's put a positive rod here. So, the rod's positive. We're told electrons, of course, are negative. So where do you think they'll go? What would you pick? Right, opposites attract. And you know what? I'm gonna go beyond that. Electrons will go here. I'll just draw a few electrons. You know what that's gonna make the bottom? Positive. When electrons leave a neutral area, that area becomes positive. Okay. Where would electrons go if a negative rod came near A, B, or C? Of course, C, because likes repel. Good, good. Negative rod touch the top of the electroscope. Which of the following would be true? So now that's called conduction, touching. And where do you think the electrons would go when that negative rod touched? Would they flow into the electroscope or flow out of the electroscope? What do you think? Absolutely, good. So let's make it. And what do you think? So once it flows in, you know what would naturally happen? They'd spread out evenly, and the answer would be A, B, and C would all be negative. E, right? So that's the only electrons move, and so now positive rod touches the top electroscope and then is removed. I bet you know this one. So now the electroscope before is negative, and now the whole electroscope is positive, right? Because we know what happens? When a positive touches, the electrons would be naturally drawn into it because opposites attract, and only electrons move. And so what you'd have electrons would leave that electroscope. It would no longer be neutral. Electrons leave, it'd be more positive than negative. So that's where would the electrons go if a positive rod came near? Well, wouldn't they be drawn to A? Because opposites attract, they would go to it. They would be drawn towards it. In fact, you know what else would happen? They'd probably come up from the bottom, and even the stuff from the ground would want to be. So they'd go towards A. Now, where would the electrons go if a negative rod came near? Actually, the electrons would actually be driven into the ground because they would want to get the negative electrons would want to get away from the negative rod, so they would be driven into the ground. All right, this is like a question on the lab. So now you've got a positive rod comes near. Let's make this positive. It doesn't touch; it just comes near. And now these are two side by side. So now electrons can move. And where will they move? Will they go from A to B or B to A because of that positive? Opposites attract, B to A. And so sphere B, okay, what would the charge in A be? The next electrons would go there, absolutely. And the sphere A would be negative. Okay, and now if sphere A is negative, what would sphere B be? Okay, what would the charge on sphere B be if sphere A is more than, what would the charge on sphere B if a positive rod came near? Positive rod, electrons would be drawn this way, wouldn't they? What would the charge on sphere B be? Okay, then it would be positive, right? Because this would be negative. All right, what would the charge on sphere B be if a negative rod? Now, if the rod is negative, the electrons will be traveled to B to be repelled by that negative rod. What would the charge on B be? That would be negative. It's like we get a little repetition. Feels like we're getting repetition. How about what would the charge on sphere A be if a negative rod came near? So this is negative. The electrons would be driven in this direction. So A would be positive. Does this all make sense so far? So let's go to something a little more challenging. So this is all about opposites attract, likes repel, only electrons move. Now this is good. I bet you know this one. The smallest of all possible charges. Good. That's the elementary charge. It's on page 1 of the reference chart. Here's a classic question. I told you, cannot have this charge. Cannot. I think you might have to get out your calculator for this one. Before you answer, what's the rule about cannot? When you divide it, you get what kind of number? Right, perfect. So not a multiple. I bet you already, without even the calculator, I bet you know which ones you can cross out. Do you see any ones you can cross out? Well, yeah, because that's 5 times 1.6. Now that you can cross out. How about another one that's a multiple of 1.6? Right, that's 2 times 1.6. Yeah, good. You got it without even doing any work. When a neutral metal sphere is charged by contact with a positive glass rod, the sphere. So let's draw a picture. What's going on here? So neutral metal sphere, positive rod. It's good to draw a picture. The sphere. What happens when that positive rod touches? The sphere will do what? Well, let me just tell you a little note. Never pick anything with protons because they don't move. Let's cross these two out, right? Never pick anything with protons because protons don't move. Let's see. Well, the positive rod touches. It says it doesn't lose electrons because the opposites attract. It will lose electrons. Get that? So never pick tomorrow gains protons or loses protons. It'll always be the wrong answer. Alrighty. Negative charged plastic comb brought close but does not touch a small piece of paper. If the comb and the paper are attracted to each other, the charge on the paper, this is a good one. So the comb is, what is the comb? Negative comb, and the paper, what do you think the paper is? Well, actually, that's close, but it could also be neutral. Because remember us saying opposites attract, likes repel, electrons repel, only electrons move and neutral attracts. Actually, the truth is, so opposites attract, opposite charges attract, like charges repel, and neutrals are attracted to both the negative and the positive. Oh, you're going to need a calculator for this one. That's actually 6 million electrons. What's the charge on 6 million electrons? See that? So you know the charge on one electron, don't you? It's 1.6 times 10 to the negative 19. But we don't have 1, we have 6. It is B. Very good. Just you multiply this 6 times 10 to the 6 times 1.6 times 10 to the negative 19. Two identical metal spheres A and B placed in an insulating stand. Sphere A is this much, sphere B is this much. They're brought in contact and then separated. What's that rule about those two charges? Now they want to find the individual charges. What do you do with those? Remember how the total charge gets distributed evenly? So all you have to do is add those two up and divide by 2. So now you know two charges. This will be on your test for sure. Two charges touch and are separated, add and divide by 2. And I think, is it B? It's B, right? And you add those two numbers and divide by 2. Do you know how to put those numbers into your calculator? So it's negative 9 times 10 raised to the power of negative 6 plus parentheses. I think you should use parentheses. Parentheses 3 times 10 to the negative 6 and a parentheses equals, and then you have to divide by 2. The charge on this is a good one. If the charge on each of the two metal spheres is doubled, the distance remains the same. What about the force? Now, what you would have to do in the test is go to the reference table and find the equation that has force and charges. That's right here. So force equals K Q1 Q2 over R squared. So both charges are doubled. Look what I did. And the change on the right equals the change on the left. So I'm plugging in changes, not numbers, but changes. So both charges are doubled. So what's about the force? 4 times greater is right. See, because your double times double is 4. So 4 times greater. Two neutral materials are rubbed together. There's a transfer charge from one to the other. Total charge of the system, well, I bet you know this one. I hope you know you cross out anything that says protons are transfer. Let's cross those out. Middle two are no good. So does the total charge remain constant or does it increase? I'll give you a hint if you want it. Conservation of charge. Beautiful. Positive charge is held near but does not touch the neutral electroscope. The charge on the knob becomes, because the electrons will be attracted to the top, leaving the bottom. This is a good one. Neutral hard rubber rod becomes negatively charged when rubbed with wool. So the rod becomes negative. Now we cross out the proton ones, don't we? So now we're down to B. Let's see, B or D. Let's see, got that. So let me explain. So if the rod is becoming negative, it's got to be the wool losing. All right. There's a question just like the one before. Remember this one? You don't have one electron. You have a whole bunch of electrons. What do you do with that number to find out how the charge on it? Because one electron is, what's that number again? 1.6 times 10 to the negative 19. So don't you just multiply that number by 1.6 times 10 to the negative 19? I think you do it again. I don't think you multiply. Do 2.5. I don't think you multiply. I think you divide it. Did you divide? You divided. It's actually B. Because try it. 1.6 times 2.5 is 4. Isn't it? Okay, a charged particle is placed in an electrical field. If the charge is doubled, the force is, let's take a look. Electrical field, E, and a charge. Well, there it is. Look at that equation. If the charge is So now we have to separate the things we're comparing. By cross multiplying, E times Q is F, right? I multiply both sides by Q. Whoops, I made a mistake here. Let me fix this. This is E times Q. So you cannot relate things till you separate them. E times Q. So now look at that. So look at that relationship. It's direct, yeah. So if the charge is double, the force is double, right? Double. An object, okay. And so we have an object has a charge, that's Q. There's a force. And look at all the choices. Do you realize, I always love this trick. Don't the choices tell you what to do? Look at the units of the choice. Newtons divided by coulombs. Don't you just take, isn't that a great trick? Then let's take the newtons that they gave us. So the answers tell you what to do. Look at that. But I use parentheses, -2 times 10 to the -6 coulombs. The answer actually tells you how to do the problem. But you better use those parentheses. It is A, I think. Okay, 2-point charges a separated distance of 1 meter and have a force of 9. What if they got closer? Now they're 3. Charges and forces. Let me see what we got here. They mentioned charges and forces. I better get an equation. This is a relationship problem, so I need an equation. The equation that has charges and separation distance is this, right? Get it from the reference table. Now, so at first it was, let's see, it was 6 meters. Whoops, my bad. There was distances 1 meter apart, and the force was 9 newtons. Now it's 3 meters apart. Right away I know it's going to be a weaker force, right? We went from 1 to 3. It's further away, so it's definitely going to be weaker. Let's cross out this guy, and it's got to be weaker. And wait a second, I actually know this answer because it's not going to be the same. It's not going to be still 1 newton. So, but let me give you the answer. So you triple the distance. Look at this relationship, right? That's inverse square. So this didn't change, so it becomes 1. Triple squared is 1/9. What's 1/9 of 9 is 1 newton. See that? You see how we did that? So what doesn't change becomes a 1. The whole top doesn't change. The bottom changes by 3. 3 squared is 9. 1/9 change on the right, 1/9 change on the left. It goes from 9 newtons to 1.
Good afternoon, ladies. If you're waiting for the Garden City bus, please go outside now. The Garden City bus is outside now.
Okay, so now this is another example of 2 charges and force, right? The 2 charges are doubled. The 2 charges are doubled. What happens to the force? So I need an equation with, force and 2 charges. So I go to my reference table. Oh, this has force and 2 charges, and both charges are doubles. Isn't that right? What they said? Let's see. Oh, my bad. One of the 2 charges is doubled. I didn't read right. One of the charges is doubled. So what's going to happen to the force? So whatever change happens on the right, double the right, double the left. Remember, whatever change happens on the right happens on the left because, it's an equality. Okay, here's another one. Now, 1 meter apart, it's F. A half a meter apart, you're getting it closer. So 1 meter apart, it's F. I'm going to make you do this one now. 1 meter apart, it's F. A half a meter apart. So what's that relationship? Oh, that's an inverse squared. This doesn't change at all. It becomes a 1. But the bottom changes what? You know what happened to the bottom? The bottom was halved. But that's squared, isn't it? What do you think the answer is? You are correct. It's D. 1/2 gives you 4 because you invert and you square. How much energy? Okay, this is V. V for volt, V and Q and energy, but actually energy is W. W equals question mark and W equals V over Q. Now this is a hard problem because we have a V and a Q, but you know what? 5 volts and I wrote this wrong. My bad. V equals W over Q. And so we have 5 volts equals W over 3.2. Now we have a problem here. All our choices are in electron volts. Remember I said J goes with C and E goes with E? We have a problem because E goes with E. this is going to be changed to 2 elementary charges because E goes with E, 2 elementary charges. Now we have a match. J goes with C and E goes with E. So now we got a match. Now we can do it. V equals W over Q. 5 volts equals W, which we want, divided by 2 elementary charges. Now I can get an answer within electron volts. So I cross multiply and I get 10. Remember that? Joules goes with coulombs. Elementary charges go with electron volts. Okay, moving Q and W. What is the potential difference V? And once again, this is on a lot of regencies, so this is really important. V is W. So the W is given 6.3 times 10 to the negative 34. And J goes with C, so we're good, right? That's 10 to the negative 4. And the coulombs is, 2 points, so we've got a match. Negative 6 coulombs. This is negative 6. So that's just a plug-in. Wait a second, I think I made a mistake. I'm sorry. I did. Oh no, this problem will be. What do you get when you do it? I did make a mistake. What's the answer? I think it must be B. Is it B? Okay, sounds good. Now, what is the energy required? W. Now, 1 elementary charge is. Wait a second. Look at the answers. They're in J. Do you remember J goes with C? So that's no good. We got answers in J, but I don't have a coulomb. But I need a coulomb, so I just say, oh, okay, I'll use 1.6 times 10 to the negative 19th coulombs. Now I'm good. J goes with C, so V equals W over Q. So V is the 5 volts equals W divided by 1.6 times 10 to the negative 19th coulombs. Cross multiply and solve. I think you get B, right? There's my V. Oh, an electron, huh? What is the minimum energy? W equals question mark. What do I use? Now, look at the choices. Unfortunately, some of them are in joules, some of them are electron volt. This is a tough question. So what do I do? Let's try to solve it saying let's try this. Maybe we could say 1 elementary charge. Let's get the answer in electron volts, see if we've got it. Ready? V equals W over Q. So V is 1.5 volts equals W, which we don't know, over 1 elementary charge. 1 elementary cross multiply 1.5. Oh, good. It turns out to be 1 electron volts. It turns out to be this guy right here. When do you have to go to red and gold? Oh, I thought you had to go. Didn't you send me an email?
Yeah, I thought I
Okay. So let's try, let's go to the big time. Let's go to 1, 2, 3 physics. I think we're ready with some 1, 2, 3 physics. Why don't you lock yourself in? And the first one, we haven't done a lot of conservation of charge. That's a good one. That's a good one. You know, you're going to see something like that. Let me give a little break, and why don't you spend about up until 5, how about do 5 minutes of these, and we'll talk. Conservation of charge, so go to electricity, and then see conservation of charge. Yeah. Electricity, so you picked electricity, then look at the second one, conservation of charge. How'd you do? So did you look at the answers yet?
Yeah.
So you've got the 12, did you add and divide by 2 in this one? Get 14?
Yeah.
Okay, another one, you add and divide by 2. Let's see, what does this say? Yeah, this would be another negative 3, wouldn't it? Because you add and divide by 2. And this one over here, let's see, then I guess when they're touched and set it's still going to be negative. They're both the same, so you add divide by 2, you're still going to get this. Unless they ask for the total charge. No, that's good. So they'll be the same charge. Once again, you add divide by 2. Now this one's harder. Do you see this is negative 5 and negative 6? So that these are not the same. What did you get? Did you get 2.1? This comes out to be, let's see, 1.2. Is that right though?
Yeah.
Okay, that's right. Yeah, I'm not able to do this in my head. And this one over here, you add and divide by 3. What does it say? Charge on each charge. So the 2, 4, 6, this is 10, 12. Each will be 4 times. So that's good. Got it. Let's see what else we can do before time. So we did conservation of charge. Let's get out of there. How about, let's see, what else is good? How about the good old elementary chart? Could be found. Which one could be found, do you think? No, 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 no. Try again. Gotta be a multiple, right? Well, try that. Take that and divide by parentheses 1.6 times 10 to the negative 19. I don't think you get a whole number. Because 2.4 divided by 1.6 is definitely not a whole number. I think if you divided this one by 1.6 times 10 to the negative 19, you get a whole number. You get 20 rather. Try this one. Yeah.
That's what I said.
Oh, I'm sorry. So sorry about that. What is the net charge of two spheres now? 3 elementary charges. Well, no, because that's actually a big. If you do the division, I think you get 20. Try that. Try 3.2 times 10 to the 18th divided by 1.6 times 10 to the negative 19. I think you get 20. Try it, don't you? Okay, net charge. What if you had 3 elementary charges? Which one's the right one? 3? Right. 3 times 1.6 times. Now, how do you do this? You have always, well, we did this one already, didn't we? 6 million electrons. Remember how we multiplied it by 1.6 times 10 to the negative 19? I think actually, do you get this? Because each electron is 1.6. Here's another one. It charges not possible. Not possible. Absolutely not a whole number. Okay, what's the charge on magnesium when it loses 2 electrons? Loses 2 electrons. So doesn't it lose 1.6 times 10 to the negative 19th? Right. Okay, you have excess of 5 elementary charges has a net charge of, I think you're right, yeah, because 8 times 1.6, yeah. So an alpha particle is positive 2 elementary charges, so its charge is absolutely the smallest of all. This is an easy one. The smallest of all possible charges. Metal sphere has a charge of that many coulombs. How many more electrons? Well, what do you do to this one? How many more electrons than protons does it have? What do you do with that number? Let's put it on a calculator. 1.1 times 10 to the negative 6. But what do we do next? To find out how many electrons, how many 1.6 times 10 to the negative 19? Right, good. Derive with parentheses. Good job. Well, I don't know. I haven't done this in my head, but trust you. Yeah, it looks like you're right about that. Which quantity has an excess of electrical charge which could be found on an object? Well, I see it. Okay. The force and force. Okay, so you want to find F, oil drop. So it's, what is it, an electron, negatively charged. Oh, this is just an oil drop could have a charge of. Okay, that's easy. Well, it's too low. That's lower than 5
Is
times the negative.
6.4?
I think it might be. 1.6 times 4. Is that 6.4? Yeah, it is. Isn't it 1.6 times 4? Okay, this one's easy. 3 elementary charges.
4.8.
But not the positive one, the negative one. Okay, a sphere has a charge of, okay, now you have the coulombs, but you want how many electrons? What do you put that in your calculator? Actually, maybe you don't even, I bet you don't need to do it. I bet you could do without the calculator. 3 electrons because it's negative. An object cannot have, right, small sphere, 5 extra electrons. You're getting good at this, aren't you? You're getting good at this. Good job. And that's it. 45. You done good, kid. Okay. Good luck. Take a second look at it tonight and you'll ace it.